Hello, I welcome you all in this presentation related to the subject materials processing fundamentals and practical, and we are talking about the welding of metals. So, in this particular presentation we will try to focus more on the arc welding processes, but before going into the arc welding process we will try to see the basic fundamentals related with the arc welding. Okay, what is the approach and the fundamental aspects related with arc welding, and then how the arc welding works for development of the weld joint with regard to the heat generation, and then what is the role of the heat input in arc welding and what are the different factors that affect the heat requirement for arc welding. And thereafter we will try to also talk about the, like say, the types of the welds, types of weld joints, okay, and welding positions. So, these are few other aspects about which we will be talking as a part of the fundamentals of the arc welding process. And the common arc welding processes like sealed metal arc welding, submerged arc welding, metal inert gas arc welding, tungsten inert gas arc welding, and plasma arc welding. So, we will try to talk about the basic aspects related with these processes too. Okay. So, as far as the approach of the arc welding is concerned, like say component to be welded like this, these are two components. So, the components, if it is thin, then even square edges can be used directly for the fusion. So, this is good enough for thin, say less than 5 thickness. Okay. So, we have to apply heat with the help of suitable arcs. So, this is arc which is generating heat. Okay. So, heat is delivered. So, when the latent heat and sensible heat combination crosses the melting point, then it leads to the melting of the fin surfaces. This melting leads to the, so the melting is the first stage. So, once the things have melted from both the sides, the molten weld pool is created. Molten weld pool is created. Since the molten weld pool is surrounded by the thermal conducting metals, so heat is dissipated from the molten weld pool to the base material which is thermally conducting. So, the heat is lost. So, as the heat loss takes place, heat loss leads to the, like say, the solidification, transformation of phase from the liquid to solid. So, depending upon the composition of the weld metal, it can be equax type. Okay, sorry, it can be epitaxial type of solidification where direct growth takes place, or it can be normal solidification where nucleation first then growth takes place for completing the transformation from liquid to the solid state. Okay. So, the basic approach here, use the suitable source of the heat like say arc in this particular process, and then arc will be used for melting the fin surfaces, followed by their solidification will be resulting in the weld joint. Now, say the melting using the suitable heat source as per the physical properties. So, what are the physical properties which are the physical properties which are important from the melting point of view? So, the first thing is the temperature that is needed for melting. So, we can say the melting temperature, in case of alloys it is the liquidus temperature, okay, and in case of the pure metals liquidus and solidus temperature both are same. So, this temperature should be low. If it is low, then it will be easier to melt, that is one. Then the second aspect is the thermal conductivity of the metal. So, like say we are applying the heat through the suitable heat source like say arc. So, heat being delivered, when the heat is delivered, a part of heat will be dissipated to the base metal. Okay. So, if the heat is transferred from the zone where heat is being applied very rapidly, then it will take longer time to attain the molten state, to fuse the fin surface, to melt the fin surfaces of the parent metal. So, that will make the job of melting little difficult. So, if the thermal conductivity of the metal, like in case of copper, aluminum is high, then we need to apply the higher heat. Okay. Heat input will be more. We need more intense energy of the heat source. So, little higher power density will be needed for that. So, the K is 1 apart from the melting point of the metal. So, these are the two important aspects. Apart from that, if the section thickness is less or section thickness is great, no, if it is very high. So, it is easier to melt when section thickness is less, it is thin as compared to the thick sections, because when the heat is applied in case of thick sections, because of the greater thickness, heat will be dissipated very rapidly away from the zone where heat is being applied for melting the fin surfaces. So, apart from thermal conductivity, melting point, the thickness of the section, thickness is the another factor that affects the heat to be supplied, and also it affects the choice of suitable welding process, choice of suitable welding process parameters, okay, because these will be governing the welding process as per their power density and the process parameters. These two will be governing the rate of heat generation and the rate at which heat will be delivered to the base metal. So, it is important that melting using suitable heat source, heat source as per the physical properties, so which with thermal conductivity, melting point and thickness. Okay. So, the another one, the metal, as I said, which has the parent metals which have been melted. Now, after the melting they will be solidifying. So, this solidification can take place through the epitaxial, when either autogeneous welding is done, means just the melting of the fin surface is performed, no separate filler metal is added. Okay. In that case, the autogeneous welding is performed, or we are using the filler metal exactly same as that of the parent metal. So, the composition of the parent metal and weld metal is same. In that case, the solidification will be epitaxial, means there is no nucleation, direct growth will be taking place. And when we use the filler metal different kind, like say this is parent metal made of say iron, and if the filler metal is used of the nickel, like say nickel filler is being used, then there is a complete difference in the crystal structure and composition. So, in that case, you see it will be first nucleating and then growth for transformation from liquid to the solid state. So, that will be the typical solidification which takes place through the nucleation and growth. So, the point here is simple. If it is the autogeneous welding, in the epitaxial solidification, or if the filler metal being used or electrode being used for the welding purpose is same as that of the parent metals, then not also epitaxial solidification takes place. But if the filler metal is completely different from the parent metals for which is being used for the welding purpose, then it will be the conventional solidification, which is nucleation and growth. Okay. Now, another interesting and important thing is, mostly the weld metal which is produced after the due to the liquid to solid transformation, mostly this occurs under very rapid cooling conditions. So, the cooling conditions, the rate of solidification is very high. Maybe in case of say TIG weld, for example, it can be less than 1 second also. So, rapid solidification results in a very fine grain structure. This is one. So, and another aspect is that it, in case of the transformation hardening metals, it can also lead to the formation of the martensite in the weld metal. Okay. So, in case of the autogeneous welding, and if you want to avoid the martensitic transformation which may be leading to the embrittlement of the weld joint, then we can use the softer filler metals accordingly. So, this is one that we basically get very fine cast structure, and this cast structure is usually having the very fine dendritic arms like this. Okay. So, interdendritic arm spacing is extremely fine in case of the welds. However, so this kind of behavior is observed not exactly at the fusion boundary, but little away from the fusion boundary, because the weld shows the 3 or 4 different types of the microstructural variation from the fusion boundary. For example, immediately after the fusion boundary, we in the weld zone we get the planar structure. okay, like this. Then we get the cellular structure. Next is cellular structure, okay, and then we get the dendritic structure like this, okay, dendritic structure like this, right. So, then so this is the dendritic structure, and in the middle we have the equaxed grain structure, okay. So, the grain structure continuously changes in most of the common fusion weld joints, from planar to cellular to dendritic and then equaxed at the center, and the same thing will be repeated on the other side, planar, cellular, dendritic and equaxed at the center like this, okay. And so, most of the time at the center we have the liquid metal, which will be full of impurities and the other low melting point constituents. So, most of the impurities usually settle at the weld center line. So, if the impurity level is too high, then sometimes it promotes the solidification cracking, okay. So, next is the, say, if you want to talk about the arc welding process. So, the how heat is generated in the arc welding process. So, let us talk about that. So, we have to use suitable power source. Then power source, the terminals will be connected to the electrode like this, okay, and another terminal will be connected to the base metal, and then between the electrode and the base metal an arc is ignited. When arc is struck, there will be flow of current from the cathode to the anode, okay, and the flow of current is basically contributes to the establishment of arc. Arc must be stable, means there is a continuous flow of current through the gap between the electrode and the workpiece. So, when the arc is established, initially there can be multiple methods which can be used for establishing the arc, like there can be touch start method where electrode is brought in contact with the surface of workpiece and then it is withdrawn immediately. So, little short circuiting will be taking place and that will help in triggering the arc initiation. The second is the field start. In case of the field start, strong electromagnetic field is established between the electrode and workpiece, and that helps in ionizing the gap between the electrode and workpiece, which in turn helps in establishing the welding arc. Say, once the arc is established and say current I is flowing and the arc voltage between the electrode and the workpiece is V, then these two parameters are basically used to calculate the power of arc, or heat being generated, okay. So, V into I gives us the power of arc. So, this is the rate at which heat will be generated per second, okay, power of arc or heat generation rate. Since the arc is moved during the welding, so not entire heat being generated will be delivered to one location, but it will be distributed at different locations since the arc is moving. So, what is the net amount of the heat being delivered, net heat being delivered during the welding? Say these are the plates, here this is the location of arc where it is struck. Once arc is stable, then heat will be generated and melting will be started, then arc will be moved at a certain speed. This speed can be very slow or it can be very high. Speed can be very low or very high. Low speed means like say 30 mm per minute, 50 per minute, or it can be 200 per minute for high speed, okay. So, there can be lot of variation in the speed at which the arc is moved during the welding. So, this speed is crucial since our heat is being generated at this rate, but it will not be delivered at that rate because that will depend upon the speed of the arc. So, if we have the data about the heat the welding speed in terms of the minute, then we can simply convert in welding speed in terms of per second, okay, this is one. So, V I by S, that is the welding speed, V I by S the welding current in arc, the V is the voltage, current is the ampere and speed in mm per second, okay. Then this will directly give us the joules per mm, that is the net heat input per. But if the heat being generated, like say the 200 is the current and the 20 is the arc voltage and the welding speed is the like say the 10 mm per second, then we will be getting like say the 400 joule per mm, Okay. So, if this is too much, then so if this is one way, another way is that we can also divide it with the 1000. What is the meaning of that? When it is divided, then we can write like 0.2 kilojoule per mm, because the net heat input is usually expressed in the unit of the kilojoule per mm. Okay. But if we have another way, like the 200 is the current, 20 is the volt, and 6, like say the 240 mm is the speed, s is the 240 mm per minute. Okay. That is per minute. So, we have to divide it with the 60 and then 1000. So, when we divide it 60, then 200 multiplied by 20 divided by 4 into the 1000. So, what will be getting, all these zeros will be cancelled, and what will have 1 kilojoule per mm, like this. Okay. So, if so the depending upon the unit in which we have the welding speed, we have to divide it with 60 or nothing is to be divided. If you want the net heat input in kilojoule per mm, then 1000 is to be divided, otherwise V I by S can directly be used. If we are divided by 1000, then we will be having kilojoule per mm. So, depending upon the speed, the welding speed can be in mm per second, or if it is in mm per minute, then we have to S by 60 is to be used. Okay. So, this is about how to determine the net heat. How much heat is to be delivered? Certainly that will depend upon these two factors, like these are basically the parent metal related, like the metal can be of the high thermal conductivity or it can be of low thermal conductivity. So, whatever heat is being delivered, that should facilitate the melting of the fine surfaces. If thermal conductivity is less, so when the heat is being delivered, it will not be dissipated much to the underlying base metal by the arc, and it will quickly help in melting the fine surfaces. So, that will be true. So, we need net heat input, we need low heat input if our thermal conductivity is less. Okay. But if the thermal conductivity is high, whenever the heat is being delivered, it will be rapidly transferred to the underlying base metal. So, it will take a lot of heat for realizing the melting of the fine surfaces. So, H net should be high, higher H net will be needed when thermal conductivity is high, and little lower H net will also be okay when we are working with the low thermal conductivity metal. Likewise, we need the net heat input, less heat net heat input is required, especially when we are handling the thin sheets, because it does not require much of the heat for melting the fine surfaces. Okay. So, basically the metal, like thermal conductivity and thickness of the section, these are the two very important parameters that dictate the net amount of the heat. Okay. So, what is the effect of the net heat input? Okay. So, let us say take the example this. So, if our heat source is being moved very slowly, then our shape of the pool will be close to that of the circular family. Okay. Okay, this is one, and if we are moving very slowly, then our lot of heat will be dissipated to the underlying base metal, and therefore, so when heat is continuously delivered at one location, then the melted area will be increasing, which means if we are dealing with the, if we are using less heat input, then the weld zone size is narrow, and the weld area, weld cross sectional area is small. But when we are supplying the greater heat input, either by using V I by S, so low heat input or high current, then these two will be used primarily for adjusting the H net, because the arc voltage primarily depends on the type of the electrode which is being used. Okay. So, for tungsten inert gas welding, this is very low, maybe 12 to 15 or maximum 20, but for the shielded metal arc welding, this can range from 30 to 100 also. For metal inert gas welding, it may be 20, 30, 40 also. So, depending upon the electrode material, the voltage can vary marginally, but the current is primarily adjusted, like say from 50 to 500 ampere. Okay. So, basically the welding current is adjusted to change the net heat input for a given speed, or we can adjust the welding speed for a given current to adjust the net heat input. Okay. So, when the net heat input is increased, what happens? The weld cross sectional area will be increasing, because we continue to supply heat at a particular location for longer time. So, this is one. The second is increasing the heat input dissipates lot of heat to the underlying base metal. So, our HZ width also increases. So, these are the two major changes which are observed with the increase of the heat input. So, if we in x axis we put the net heat input, say 0.5 kilojoule, kilojoule per mm or 2 kilojoule per mm, there is a great difference. So, that our cross sectional area will be increasing almost linearly in the beginning, weld cross sectional area. Okay. And likewise, our heat affected zone width also increases, HZ width will also be increasing. So, here we can say the weld characteristics in the y axis, HZ width increases with the increase of net heat input, and weld cross sectional area increases with the increase of heat input. So, these are the two major changes take place, and we know that increasing weld cross sectional area, this simply increases the residual stresses, this is one, and increasing HZ width increases the thermal damage that will be taking place in the material characteristics due to the microstructural changes or due to the degradation in mechanical properties that will be taking. So, a higher heat input is not considered to be good. That is why we have to supply the optimum amount of heat which is good enough for producing the sound weld joint, but that is not much to cause unnecessary thermal damage of the metal. This is just for an example how to calculate the net heat input. So, say if for different welding currents, say if you are using 3 sets of the examples, the welding current I in ampere, say 120, arc voltage is 12, welding speed is say 100 per minute. Then the arc power is simply Vi obtained from the Vi, then 12 into 120, that will be giving us 1440 joules, and if we convert this into the kilojoule, it will be 1.44 kilojoule. Okay. If we are interested in determining the net heat input H net, then Vi divided by S has to be used, and so here the Vi since the welding speed is in the minutes. So, we have to use that Vi by S divided by 60 into 1000 kind of formula. So, here we have 120 multiplied by 12 multiplied by 60 divided by 1000 and divided by 100. Okay. This will be giving us this much net heat input. Likewise, we can use 250 welding current, 20 arc voltage, 150 welding per minute to welding speed. This will be giving us the 2 kilojoule. So, by changing the welding current and by changing the welding speed, we can adjust the net heat input significantly. So, if you can see here, by using the different set of the welding conditions, we can change the net heat input significantly. Now, we will be talking about the types of the weld and the edge preparation. Like when we are doing the welding of very thin sheets, then we need to just make the edges square only, that is all. But if we are dealing with the thick sections, then through thickness penetration cannot be realized in one go, therefore, edges of the sheets must be prepared by removing the extra material. So, we can prepare the edges in different ways. So, edge preparation has a much wider scope, not just the cutting and preparing the edges, but also the cleaning and removing all impurities. Okay. So, initially we will talk about the different types of the weld. Different types of the weld means how the weld metal is deposited. It is about the weld metal deposition. Okay, how it is being deposited. It is not about the type of the joints. So, when we have the groove like this, whether it is a square or V, in the groove metal is filled, then we simply call it as a groove weld. Okay. So, these are the different types of the grooves like V groove, U groove, B well groove or the J groove. Okay. And metal is simply filled in this. So, when it is a square, so we can say these are the groove welds. Okay. And when we prepare, the edges can be prepared. So, it can be, if no edges are prepared like this, simple metal is deposited by melting little bit base metal, then this is the fillet. Okay. But if the edges are prepared one side like this, then it will be groove weld. Okay. This is the difference. So, if we prepare a groove and then it is filled in, then it is groove weld, and if there is no edge preparation, then it is fillet weld. Okay. Then the weld metal can also be deposited over the simple plane surface like this. Okay. This is called the bead weld, where just little bit melting is realized for good metallurgical bond. But this is, so in this approach what we do, we try to develop a layer of a good quality material over the surface of substrate, which is of relatively cheaper or low quality. Like say, over the mild steel we can deposit a layer of austenitic stainless steel for good corrosion resistance. Okay. So, this is an approach where a simple layer of the molten metal is deposited, molten weld metal is deposited by passing the different beads over the surface of the metal. This is called the bead weld. Okay. So, we have seen groove weld, fillet weld, bead weld. Apart from that, we have two more types of the welds, like where the plug weld or slot weld. So, in this case, in both the cases, we may, like say, this is the bottom plate and this is the top plate. So, we make the groove, this is circular. So, this circular groove is filled in by the molten metal by partially melting the lower sheet. Okay. So, in this case we call it as a plug weld, and if the shape of the groove in the being made in the top plate is rectangular, then we say it as a slot weld. Okay. So, this is about the type of welds, which is based on the way by which the weld metal is deposited. So, this is the top plate, bottom plate, and the groove is made in the top plate. If it is circular shape, then it is called plug weld, and if it is rectangular shape, then it is slot weld. So, after making this kind of the groove inside the top plate, it is filled in by the weld metal to produce the plug or the slot weld. Okay. Now, there are various terminologies which are used when a weld joint is made. So, we have say parent metal or the base metal, two sides, then a groove has been made like this. Okay. Okay. So, this is called single V groove weld joint, and the type of the joint is the butt joint, about which we will be talking in the next slide. Okay. So, when partial melting of both the metals is done, okay, and then what we do, deposit the weld metal. So, we have the depth up to which the base metal is melted is called depth of penetration. At the bottom side, the gap between the two plates at the bottom side is called root opening, and this section is known as root face. Okay. The depth up to which the base metal melts on the groove surface is called the depth of fusion. Okay. This is the weld zone where the molten weld metal was placed or deposited, and then it has solidified. The top surface is called weld face. The width of the weld at the top is known as weld width. Okay. And the height of the weld above the base metal surface is called weld reinforcement. Okay. And the connection between the weld and the base metal, so this junction point is called the weld toe, and weld toe, if it is of the low angle like this, then this is less troublesome because of the lower stress concentration. But if the weld toe is high like this, then high bead angle causes the greater stress concentration, and therefore, most of the time the crack tend to start from this location and propagate either into the weld or in the heat affected zone. Okay. So, these are the various terms related to the weld joint. Okay. So, here I will conclude this presentation In this presentation, basically I have talked about the fundamentals related with the arc welding and how the heat generated and how we can get the net heat input, and how net heat input can be adjusted by changing the welding parameters, and what are the different types of the welds. Thank you for your attention.